If there is any place in America that feels like a giant furnace, it is Nevada. The average annual rainfall here is only about 178 millimeters, even lower than many African deserts. Meanwhile, the sun and hot winds pull more than 2,500 millimeters of water out of the ground every year. In other words, nature is taking away 14 times more water than it gives. But the numbers are only the surface of the disaster. The lifeline of the entire West, the Colorado River, the water source for about 40 million people and an economy worth more than $1.4 trillion, is shrinking at an unprecedented rate. Based on tree ring analysis of ancient trees, scientists confirm that this region is experiencing the most severe drought in 1,200 years of recorded history. The consequences are clearly visible at the two largest reservoirs in the United States, Lake Mead and Lake Powell. In the summer of 2022, their water levels dropped to only about 1/4 of their designed capacity. What emerged from the lake beds sent a chill across the nation: metal barrels containing bodies from the era when the mafia ruled, and even military shipwrecks from World War II lying exposed on cracked earth like scenes from an apocalypse movie. However, the real danger still lies ahead. Engineers are racing against time toward the critical mark of 272 meters, the threshold known as dead pool. When water levels reach this point, the Hoover Dam will completely lose the hydraulic pressure needed to release water, meaning more than 2,000 megawatts of clean electricity will vanish in an instant. The Colorado River will nearly stop flowing downstream, and the entire water supply system of the American West will begin to collapse. The impact will spread like a domino effect. The fertile agricultural regions of California and Arizona, which feed tens of millions of people, could turn into dead land within just a few growing seasons. Faced with this reality, scientists are forced to admit a bitter truth. This is no longer a drought that can be reversed by a few years of heavy rainfall. The American West is slowly sliding into a long-term process of desertification, and there may be no way back. In this context, every water-saving measure becomes powerless. Cutting agricultural irrigation, which accounts for as much as 80% of the Colorado River's water use, is like using a small bandage to seal a wound that is spurting blood. And from this desperation, an idea once considered insane has begun to be discussed seriously. If the sky no longer delivers rain, why shouldn't humanity bring the ocean deep into the continent? The heart of the project lies along the California coastline, where massive desalination superplants are planned at an unprecedented scale. Instead of pushing raw seawater deep inland, which would violently corrode pipelines and create irreversible soil salinization risks, the entire treatment process is carried out directly at the source. The core technology is reverse osmosis, using ultra-high pressure of around 1,000 pounds per square inch to force seawater through semi-permeable polymer membranes, where only water molecules are allowed to pass while salt, bacteria, heavy metals, and microorganisms are trapped. Thanks to next-generation membranes combined with graphene and pressure recovery systems, each cubic meter of fresh water today consumes only about 3 to 4.5 kilowatt hours of electricity, nearly half the energy required 2 decades ago. Although reverse osmosis has already been commercialized in places such as the Carlsbad plant in San Diego, the Nevada project would be dozens of times larger in scale, bringing severe risks of membrane clogging by algae and organic matter. This requires a complex pre-treatment chain, from sand filtration and nanofiltration to continuous biological removal. Maintenance costs for the membrane system alone could account for 35 to 40% of total annual operating expenses, equivalent to hundreds of millions of dollars per year at this mega project scale. The design breakthrough lies in the pipeline route. Instead of cutting through protected natural reserves or displacing dense residential areas, the system is proposed to be buried along the corridors of Highway 95 and abandoned railway lines. taking advantage of existing infrastructure rights-of-way to reduce legal conflicts and ecological impact. Along this route, booster pump stations would be installed every 80 to 120 kilometers, paired with an ultra-high voltage power transmission network. The main pipeline is expected to have a diameter of 6 to 8 meters, nearly the size of a subway tunnel, capable of transporting more than 200 cubic meters of water per second. Pressure in uphill sections would exceed 150 bar, requiring reinforced carbon steel composite alloys, similar to those used in transcontinental gas pipelines. The pumping route would cross the Mojave Desert, following ancient fossil riverbeds, with gentle slopes to penetrate deep into the Nevada Plateau. The greatest challenge, and the focal point of opposition, is gravity itself. Nevada sits on the Great Basin Plateau, where target valleys lie at average elevations between 1,000 and 1,700 meters, while the Sierra Nevada Range and coastal mountains form massive topographic walls separating the ocean from the interior. According to the laws of thermodynamics, the energy required to lift such enormous volumes of water to these heights is unavoidable. Pumping 1 million cubic meters of water up roughly 1,200 meters already requires power on the order of thousands of megawatts. To maintain flow rates sufficient to form artificial inland lakes, the system would need to operate continuously at 6 to 8 gigawatts of electricity, equivalent to the output of 6 to 8 large nuclear reactors, or the entire power demand of a megacity with several million residents. Compared to this, the Hoover Dam's maximum capacity of about 2 gigawatts is like a spoonful of water in the ocean, meaning at least 3 to 4 Hoover Dams would be needed just to run the pumping system. If the electricity came from fossil fuels, the project would emit more than 20 million tons of carbon dioxide each year, comparable to the emissions of a small country, turning a drought relief plan into a new climate disaster. It is at this deadlock that engineers propose transforming the desert into a colossal energy factory, deploying solar power belts across hundreds of square kilometers, combined with high plateau wind, to generate 10 to 12 gigawatts of renewable capacity. At the same time, the artificial lakes themselves would serve as pumped hydro energy storage systems to store electricity overnight. In other words, water generates power. Power lifts water upward, a closed energy loop never before attempted at a continental scale. California and Nevada are the two leading U.S. states in renewable energy, especially solar power. California currently has more than 42 gigawatts of solar capacity, while Nevada is aiming for 50% renewable energy by the year 2030. However, the rapid expansion of solar power has created the famous duck curve. During the daytime, when the sun shines at its strongest, electricity production becomes so excessive that the grid cannot absorb it all, forcing operators to curtail output or even sell power at negative prices. In contrast, when the sun sets in the evening, household demand surges while solar supply disappears, requiring expensive and polluting gas power plants to fill the gap. The lack of large-scale energy storage systems is the fatal weakness of the Western power grid. The Pacific Water Transfer Project is designed to solve this exact problem through pumped hydroelectric storage technology. Instead of being just a one-way water pipeline, the system will function like a gigantic battery. The operating mechanism works as follows. 1. Pumping phase. Charging the battery. During the day, when solar electricity is abundant and cheap, the system uses this energy to run massive pumps, pushing water from sea level up to intermediate mountain reservoirs or directly into storage lakes in Nevada. At this stage, electrical energy is converted into the gravitational potential energy of water. 2. Discharge phase, releasing the battery. At night or during peak demand hours when the grid is short on power, the elevated water is released downward through high-pressure pipes, spinning turbines that generate electricity back into the grid. With round-trip efficiency of about 70 to 80%, This technology is far more effective than building massive lithium-ion battery farms for power storage. The project turns Nevada into a regional energy warehouse for California, stabilizing the southwestern grid. The enormous energy cost of pumping water is offset by the price difference between peak and off-peak electricity, while simultaneously solving the problem of renewable energy oversupply. Even with an energy solution in place, the $16 billion upfront investment remains a massive financial barrier if the project relies solely on clean water sales. The golden key to financial viability lies in a byproduct of desalination waste brine. In the reverse osmosis process, every 2 liters of seawater input produce 1 liter of fresh water and 1 liter of highly concentrated brine. Traditionally, brine has been treated as hazardous waste. Discharging it directly into the ocean can increase local salinity, kill bottom-dwelling organisms, and destroy marine ecosystems. But in today's economy, brine is essentially liquid ore. When seawater is concentrated, the levels of valuable minerals double. The world is shifting into the era of electric vehicles and green energy, and lithium, the lightest metal, is often called the new oil or white gold. Lithium is an irreplaceable component of lithium-ion batteries. However, the global lithium supply chain is currently dominated by China and South America. For the United States, securing a domestic lithium supply is a matter of national security. Seawater contains lithium, magnesium, rubidium, boron, and uranium. Although lithium concentrations in seawater are lower than in salt flats in Chile or Argentina, the enormous volumes of water processed daily in this project would yield massive total output. The Nevada project proposes integrating direct lithium extraction technology directly downstream of the desalination plants. DLE uses selective adsorption materials to capture lithium ions from brine without waiting months for evaporation, as in traditional methods. This economic model is already being proven in the Salton Sea region of California, now known as America's new Lithium Valley. Major players such as Berkshire Hathaway Energy, General Motors, and Energy Source Minerals are investing billions of dollars to extract lithium from geothermal brines with estimated reserves of 600,000 tons per year. If this model is applied, the Nevada project will no longer be a money-draining water infrastructure scheme, but a highly profitable mining energy complex, with fresh water becoming a low-cost byproduct dedicated to environmental restoration. Although the energy and economic arguments sound highly convincing, the project has triggered fierce opposition from ecologists. They warn that brutal interference with nature will lead to unpredictable consequences, and the clearest evidence lies right in California, the Salton Sea. The Salton Sea is California's largest artificial lake, formed by an engineering accident in the year 1905. When a levee on the Colorado River collapsed, allowing water to flood into the Salton Sink Basin continuously for 2 years. In its early decades, it was a tourism paradise, attracting more visitors than Yosemite. However, because it is a closed basin with no outlet to the ocean, the only way water can leave is through evaporation. As water evaporates, salt and dissolved chemicals remain behind. After more than a century, the salinity of the Salton Sea has now reached 74 parts per thousand, twice as salty as the Pacific Ocean. The result is a full-scale ecological disaster, mass die-offs of life. Fish die in huge numbers due to high salinity and eutrophication, where algae blooms strip oxygen from the water. Decomposing fish carcasses produce overpowering stench and toxic hydrogen sulfide gas. Toxic dust. As inflows decline due to drought and reduced Colorado River allocations, lake levels drop, exposing the lakebed filled with toxic sediments, including arsenic, selenium, and the pesticide DDT accumulated from agricultural runoff. Desert winds sweep this fine dust into the air, creating poisonous dust storms. Public health hospitalization rates for childhood asthma in the Imperial County area near the Salton Sea are twice the state average. Scientists fear that the Nevada Inland Sea Project could create a chain of new Salton seas. The salt trap. Even though the inflow water would be filtered seawater, evaporation rates in the Nevada desert are extremely high, ranging from 2 to 3 meters per year. Over time, salt from the soil and minerals washed down from surrounding mountains would accumulate in these lakes. Without an outflow to flush salt away, the lakes would inevitably become saline again and turn into dead bodies of water. Evaporation losses. Maintaining hundreds of square miles of open water in the desert requires constant pumping to replace massive evaporation. If the project shuts down for economic or technical reasons, the lakes would dry up, leaving behind crusts of salt and toxic chemicals that would become new dust sources spreading across the West. Another less discussed but extremely dangerous risk is the transformation of dryland ecosystems. The lake effect. A large body of water would increase local humidity. This may sound beneficial, but for desert animals adapted to arid conditions, higher humidity creates ideal environments for disease-causing bacteria and fungi. Invasive grasses. Water and moisture would trigger the spread of invasive plants, especially cheatgrass. This grass has a short life cycle. It grows rapidly in spring thanks to moisture, then dries out in early summer, forming a thick layer of highly flammable dry fuel. The fire cycle. In the Mojave Desert, natural wildfires are rare because vegetation is sparse. But the explosion of cheatgrass turns the desert into a fuel depot. When fires occur, they burn slow-growing native plants such as Joshua trees and giant cacti. These species cannot recover after fire, causing native ecosystems to be completely replaced by invasive grasslands. The Amargosa Valley region is home to one of the rarest fish species on Earth, the devil's hole pupfish. This fish lives in a single flooded cave, isolated from the outside world for thousands of years. Changes in groundwater pressure, or water leakage, from the project could alter the chemistry and temperature of this fragile habitat, pushing the species into immediate extinction. If this plan becomes reality, it will not only transform Nevada, it could rewrite how humanity confronts the global water crisis. This is no longer the story of a single desert state, but the largest experiment ever conducted in whether humans can redesign entire ecosystems at a continental scale. Once the first pipeline is laid, we will cross a new boundary from adapting to nature to actively restructuring it. But every massive system carries massive inertia. If successful, Nevada could become the energy, water, and mineral hub of the 21st century. If it fails, it will stand as a warning that some of Earth's equations cannot be solved by money and technology alone. And as climate change grows harsher, decisions like these will no longer be luxuries. They will be survival questions. Perhaps decades from now, people will look back and say this was the moment humanity chose to become the engineer of the planet. Or this was when we learned that the greatest power is not changing nature, but understanding our limits. The future of the Nevada desert, and perhaps of the entire American West, is being shaped starting today.